Hello and welcome back to another EMAC Science Support Team tool tutorial. Today we're going to be going over the Exoplanet Boundaries Calculator. So go ahead and navigate to the EMAC website and scroll down to the Exoplanet Boundaries Calculator tool and click Launch to open up a new tab with the tool. As can be seen from the descriptive paragraph, the Exoplanet Boundary Calculator uses a classification scheme that distinguishes exoplanets into different categories based on their size and incident stellar flux. If we look at a blown up image of this chart here, we can see that based on a planet's radius and the amount of stellar flux it actually experiences from its host star, exoplanets can be categorized into different subcategories, such as small hot planets such as Venus, Mercury, to large hot planets like hot Jovians, to small cold planets like snowballs, or large cold planets like cold Jovians, and anything in between. If we go back to the tool, you can see that there are some instructions to tell you that there are limits on the Earth radius, mostly because there have not been many exoplanets discovered outside of this range. And if we want to actually try and use the tool, all you have to do is type in the planet's Earth radius, how many Earth radii it is, the temperature of its host star, we'll say 6,000 degrees, and if you know the flux it experiences or the distance from its host star that the planet exists at, you can enter that. If you don't know that, you can leave no distance information and leave this entire field blank and calculate. If you don't know how far away it is or how much flux it actually experiences, then instead of having a single point of where the planet exists, it'll have a bar line that will show you where the planet exists depending on how far away it is from its host star or how much stellar flux it actually experiences. Now let's say we do know that the planet is 1.2 astronomical units away from its host star. Based on the planetary radius and the stellar temperature and how far away it is, you can now calculate exactly where this planet exists inside of this graph. Now, as we can see, it sits at 1.75 planetary radius, and in between the H2O and CO2 lines. Now, these lines separate these different categories based on the temperature and mass regime where these different chemical compositions would condense in the atmosphere of the planet. If we go back to this chart here, you can see that Earth exists after the line of where H2O condensates in the atmosphere, and we know that that is true because Earth has water in its atmosphere. Now, this fake planet that we've created, it exists right around the 1.75 planetary radius in between the H2O and CO2 lines, so that means we would categorize it as a super-Earth. It's right on the cusp of being between super-Earth and sub-Neptune, but we'll go ahead and call it a super-Earth just based on the chart. Now, let's say we wanted to know exactly at what condensation flux boundary this planet would sit on the H2O line. So if we change this from semi-major axis to stellar flux and change this value from 1.2 to 1.15, as detailed here, you'll actually see that the planet exists directly on the line of H2O. We can do the same with the CO2 line if we change it to 0.320 stellar flux. And as you can see, it sits right on that CO2 line. This is a very handy tool for easy categorization of exoplanets based on how far away they are from their host star and their size. Another great aspect of this tool is that you can actually download the table of planetary radius and stellar flux boundaries, as well as a table of coefficients used in the calculations. If you ever want to use this tool, please consider citing this paper as well as this astrophysics journal link. Everything you need can be found on the EMAC website. Thank you very much.